In the last video about finding volume of a two-dimensional figure that's rotated around a line to create a three-dimensional object, we did a horizontal line that we did our rotation around, which is going to be the easiest way that people can do it because it's much more intuitive uh, because you can kind of leave things in terms of y is equal to x and your interval is going to be on the x-axis and things like that. But now what we're going to be taking a look at is we're going to change where the line of reflection is going to be. So here I'm sorry, not line of reflection, but rotation. So now the line of rotation is going to be across some vertical line somewhere on the graph. And so that means you're going to be integrating something along the y-axis. Now this is going to cause us to have to, make sure that we pay attention to a couple of things. Because we're going to be integrating along the y-axis, essentially what we need to do, we need to take our functions and solve them in terms of x. And from here, our interval, the interval will be along the y-axis instead of the x-axis. And when we do our integration, instead of saying dx, we'll say dy. Whatever we have for our integrand, we'll do it with respect to y. Now, looking at the functions that we have, and I encourage you to go ahead and try and pause the video and see if you can work this one out ahead of me, but presuming that you've done that, then great. Let's just see what we got. If you didn't do it, then let's follow along and see how we're going to approach this. So the first thing I'm going to notice is that I have a parabola that I need to graph. Y is equal to the square root of x, which is a pretty easy function to graph. You just kind of have something that looks like this. We're not looking for anything specific. Okay. And we have our other boundary line that makes up our region of y is equal to 4. So we just have some kind of horizontal line here. Now this is going to bring us to, we want to make sure that we can identify our points correctly. So we have 3 points that we're kind of interested in. The one on the far left is going to be at -2 and 4. The one at the bottom is going to be at the origin, 0, 0. And all of this is just based off of, concepts with being able to graph basic parent functions and understanding where the points are going to be from the vertex and so on. So the region that we're going to be revolving is going to be this region right here. So imagine that spinning around the line x is equal to 3, something like that. Now the one thing that we want to do before we get too much further into this is because we're solving this in terms, or we're going to be integrating this along the y-axis, we need to go back and do that, take our functions and solve them in terms of x, particularly the quadratic parent function. So if I took the quadratic parent function and I solved it in terms of x, I'm going to get x to be equal to essentially the positive and negative square root of y. So let me go ahead and just kind of identify where those are going to be. Let's take a brighter color. So this side of the parabola, is going to be the positive square root of y. And the other side on the left, this would essentially be the negative square root of y. And that's going to be important when we identify our inner and our outer radii. So let's see where those lines are going to be, what the length of those radii are going to be. So let me pick a different color here. Now the inner radius is going to be made from the line of rotation to the boundary, the part that makes up our function here. So this is going to be our inner radius. And our outer radius is also going to go from the line of rotation, but it's going to go to the far end of the function. So this is going to be our outer radius. So what are those lengths going to be? Well, the outer radius is going to be the difference of the line of rotation and the boundary that it intersects. In this case, I'm going to say 3 minus negative radical y, which would give us 3 plus y, or not plus y, but radical y. And if you notice, because of the change of having it rotated horizontally, like we saw in the previous video, to being rotated vertically, like we're seeing now, the difference that we do for our inner and our outer radii is done a little bit differently. In the previous video, we subtracted the line of revolution from the function itself, and here it's the opposite way. So now let's take a look at the inner radius. So the inner radius is going to be from the line x is equal to 3, and now we're going to subtract the positive square root of y, and so that's all we wind up getting is just here are our two radius lengths. And of course this is still going to be done with the washer method because we're going to have cylinders that have the interior region of the cylinder removed. Now let's see if we can go ahead and start doing our integration. Now we're still going to be using the washer method, so we're going to say volume is equal to pi times some region from A to B for the interval, and we're going to say the outer radius squared minus the inner radius, and that should be a lowercase r. Trying to write an uppercase r again. The inner radius squared, and in this case we're going to do it with respect to y, so dy. So let's start plugging in what we have. And the one thing that I didn't clearly identify straight away before we go too much further is what's the interval? Well, the interval is going to be done along the y-axis. So the interval is this bit right here. This is where the interval comes from, and it's going to be from when y is equal to 0 to when y is equal to 4. So we have pi times the integration from 0 to 4 of the outer radius, which is going to be 3 plus square root of y squared minus 3 minus square root of y squared dy. Now go ahead and simplify everything that you can inside of the integrand. So when you expand the binomials and distribute everything inside of them, the 3 plus square root of y squared is going to give you a 9 plus 6 radical y plus y minus, and when I expand and distribute the 3 minus radical y squared, I'm going to get a 9 minus a 6 radical y plus y dy. And then you distribute the negative sign in, and when you distribute the negative sign in, you can see that the, let me go ahead and just pick a different color here. When you distribute the negative in, you're going to get a positive 9 and a negative 9 that are going to cancel, a positive y and a negative y that are going to cancel, and the only thing that's going to be left over is a positive 6 radical y here, and the negative is going to make this a positive 6 radical y here, So when I do my simplification of my integrand, all we're left with is a 12 radical y. So we have 12, and if you want to, you can just say y to the 1/2 power. That makes it easier to do your integration because or your antiderivative, because now we're going to be this point we've simplified everything that we can for in the integrand, so we do the antiderivative at this point. Now, one quick thing that I noticed is that I do have 12. I have that as a constant, so I'm going to go ahead and pull that out as a constant like I would with the pi. So I'm going to have 12 pi interval from 0 to 4, and then we'll say y to the 1/2 power dy. And now is where I want to go ahead and do my antiderivative. So I'm going to get 12 or 12 pi, and the antiderivative of y to the 1/2 power is going to be 2/3 y to the 3/2 power, evaluated from 0 to 4. So now we can do our substitution. And then we're going to get 12 pi. And in this case, if you wanted to go ahead and pull out the 2/3 as a common factor, or as a common factor, you could also, but I think the arithmetic is going to be, simple enough here to do it. If you know what, let me go ahead and just pull out that 2/3 now. So that would be 8 pi here, and we would just substitute the y, so that'll be 4 to the 3/2 power. And substituting y isn't going to matter, it's just going to become, or substituting 0 is just going to make everything 0 when I substitute 0. And let me just try to clean up my handwriting here. There we go. So 4 to the 3/2 power is going to be 8. So I'm going to get 8 pi times 8, giving me my volume to be 64 pi cubic units, whatever they happen to be. And the last example that we're going to take a look at in this video, again, feel free to try to work out the problem in advance of me. But if you have done so, great. If you haven't done so, then please go ahead and follow along. Here, this one's going to be a little different because of the boundary line that we're going to be taking a look at. So we have y is equal to 2 times the square root of x. So that's going to give us our square root function like what we saw in a previous video, where the normal square root function kind of does one of those things. Okay, but because of the 2 there, that's going to act as a vertical stretch on our function. So when we graph it, we need to kind of stretch it vertically like so. And so now let's take the other line. Let's do that color here. We're going to have something like that for our line y is equal to x. And the region that we are looking for is this bit here. So that is going to be, that little sliver of blue is what is going to be taken and revolved around the line x is equal to -2 here. So now we have to be able to establish what the inner and the outer radius is going to be. So the outer radius, you can see, and let's go to a darker color here for the radius. The outer radius is going to be all the way to the line y is equal to x. That's the boundary that is going to be furthest away from the line of rotation. So that is going to be your inner radius or your outer radius. And the square root function is going to be your inner radius. And you can see here where the interval is going to be. Well, let me go ahead and clean that up a little bit here. The interval is really going to be from where this intersection is here and the y-axis, or the x-axis. So here at this point, we're at 4, 4. So from 0 to 4, our interval is going to be 0 to 4 on the y-axis. So now let's take a look at the uh, radii. So the outer radius is going to be the line of rotation, meaning -2 in this case, and I'm going to subtract the boundary line that it intersects, which in this case, oh, and I'm forgetting something, we need to solve in terms of x. There's that extra little thing that you have to remember when you're revolving around a vertical line as opposed to a horizontal line. Now, in this case, we don't really have to do much uh, with the linear parent function, because this is still just going to be x is equal to y. We don't really have to do anything with that there. But when I solve the square root function in terms of x, and I keep hitting something on my monitor, here we're going to say x will be equal to 1/4 square root of y. Nope, nope, I did that wrong in my head. That'll be 1/4 y squared. There we go. That sounds better, because when you undo a square root, you should get something squared. Okay. So now we have both of our functions in terms of x. So the outer radius is going to be the line of rotation, -2, minus the linear function, which in this case would be minus a y. And that doesn't simplify at all, so that's the outer radius. And the inner radius is going to be made from the line x is equal to -2 minus the 1/4 y squared. And again, that one also doesn't simplify. So that is the expression that we'll use for our inner radius. Again, we're looking at using the washer method. So our volume, in this case, will be, and let me not use the same color here. Let me pick a different color to change things up. So we'll say volume is going to be equal to pi times the integral, in this case from 0 to 4 is our interval. Our outer radius is going to be -2 minus y squared. And then our inner radius is going to be -2 minus 1/4 y squared, all with respect to y. So expand the binomials and distribute. And when you expand -2 minus y squared, you're going to get a 4 plus 4y plus y squared. And when you expand the second binomial, -2 minus 1/4 y squared, we're going to get in parentheses 4 plus y squared plus 1/16 y to the 4th. And I'm running out of space on the end there, but you just add the dy at the end. And now let's go ahead and distribute the negative and see what winds up happening. And you can see, very similar to the last example, that here, this +4 And you can't really see, that's not much of a difference there. This positive 4, this will become a negative 4. Those are going to wind up canceling. At positive y squared, this will become a negative y squared. Those will wind up canceling. So the 4 and the y squareds are going to wind up going away, leaving me with, I keep hitting the wrong thing for my color, pi times the definite integral from 0 to 4, and we'll have 4y, and then we'll say minus 1/16 y to the 4th dy. Now, if you wanted to, you could get a common, uh, greatest common factor here, 1/16. It would probably work out, but I'm not going to bother trying to get a common number to factor anything out at this point. We're going to just go ahead and take the antiderivative at this point. So the antiderivative of 4y will be 2y squared, and the antiderivative of negative 1/16 y to the 4th will be a negative 1/80 y to the 5th, evaluated from 0 to 4. And now you can start doing your plugging and chugging and see what the arithmetic gives you. So we have 2 times 4 squared. Oops, getting ahead of myself here. Combining my parenthesis and my exponent together. And minus 1/80 times 4 to the 5th power. And then, of course, substituting 0 into either of those won't give me anything, so we can close up the parentheses there. And here, 2 times 16 gives me a 32. 4 to the 5th power is going to be some number I don't remember, but I have it written down as 64/5. And then when you combine those with a common denominator, should you be doing that, you're going to wind up with 96/5. And that won't really simplify any further. You just distribute the pi in and you'll get volume is equal to 96 pi over 5 cubic units, whatever they happen to be. And that's going to wrap up the lesson on volume about a line. Keep in mind, particularly with these examples, if you're revolving it around a vertical line, you need to solve your functions in terms of x, and your interval will be along the y-axis, and all of these are going to be done using the washer method approach. So that's going to wrap it up. Ladies and gentlemen, thanks for watching. Take care. Be good.